My name is Eleni Katragou. I'm an atmospheric physicist and I use regional climate models for the investigation of climate change across Europe. Climate of a particular region could be defined as its average weather. It represents the accumulation of daily and seasonal weather events over a long period of time. The concept of climate also includes the extremes of weather, like the heat waves of summer and the cold spells of winter. If we were able to watch the Earth for many thousands of years, we could see that climate changes. Paleoclimatologists have shown that since the formation of Earth, climate has periodically shifted from warm to cool and back again, sometimes dramatically. Why the Earth's climate changes naturally is not totally understood. Many theories attempt to explain the change in climate, but no single theory alone can satisfactorily account for all the climatic variations of the past. The most important natural forcing affects the Earth's climate is the delivery of solar radiation. Milankovitch was the first to propose the idea in the 1930s that the Earth's orbital variations determine climatic patterns by modulating the amount of solar energy reaching the Earth's surface. Volcanic eruptions is another example of natural climate forcing. During volcanic eruptions, fine particles can be ejected into the stratosphere, absorbing and reflecting back to space a portion of the sun's incoming energy, affecting thus the radiation balance in the atmosphere. There is also serious evidence that anthropogenic activities are responsible for altering climate. During the past century, humans, as a result of burning oil and changing land cover uses, exert anthropogenic forcing into the climate system. The important question raising is, how can we quantify the impact of human activity on climate? Answering this question involves a great deal of research combining long-term monitoring of the atmosphere and numerous modeling studies of the Earth system. The most credible information on climate change is provided by an international body called the Intergovernmental on Climate Change, or simply IPCC. The fifth IPCC assessment report, released in late 2013, confirms with even more certainty than in the past that it is extremely likely that the changes in our climate system for the past half a century are due to human influence. Multiple lines of evidence confirm that the extra heat being trapped by greenhouse gases is warming the Earth's atmosphere, heating and acidifying the oceans, raising sea levels, and melting ice caps and glaciers. But how can we quantify the extent of human-driven climate change, and most importantly, how can we make credible projections for the future and assess impacts of climate change? Let's go back for a minute and inspect the components of our climate system. As one might expect, the atmosphere is one of the 6 major climate components instrumental in determining the status and trend of climate at a particular time. The climate system is also comprised of the marine and terrestrial biosphere, being the global sum of all ecosystems, the lithosphere, including mechanisms such as the volcanoes, the cryosphere, with all ice bodies and glaciers controlling the Earth's reflectivity, and the hydrosphere, including all water bodies storing and relocating sun's energy. Recent interpretations of climate include also human activity as a 6th climate component, justified by the ability of human industrial society to alter present climate by changing atmospheric composition. The state of climate can thus be parameterized as an interaction between the numerous physical, chemical, and biological processes occurring within the climate system without neglecting the multiple and complex feedback mechanisms involved. The tools we use to describe the whole Earth system are called climate models. General circulation models, or simply GCMs, use mathematics and the laws of physics to describe the general behavior of the atmosphere. To reduce some of the atmosphere's complexities, the models make assumptions and describe the atmosphere in more simplified physical terms. A GCM represents the atmosphere by dividing it into grid squares, usually 100 kilometers on a side. The number of cells in the grid system is known as the resolution. The higher the resolution, the more accurate the calculations become. On the other hand, simulations with higher resolution require more computational time. As a rule of thumb, for refining the horizontal resolution by a factor of 2, 8 times more CPU time must be considered. A regional climate model can be nested through a lateral buffer zone to a GCM through a process called dynamical downscaling. And this way, it delivers even more spatially refined climatic information in the order of 10 kilometers. To summarize, therefore, from the first assessment report of the IPCC during the 90s until the upcoming fifth assessment report in 2013, climate modeling has developed enormously by firstly coupling different climate components into one modeling system, secondly by developing more sophisticated algorithms to describe the complex atmospheric processes and the multiple feedbacks, and thirdly by reducing the spatial resolution of climate simulations from about 500 to less than 100 kilometers in GCMs or even to 10 kilometers in regional climate models. As one might expect, the scientific development increases considerably the demand in computing power and storage resources. This is how the European grid infrastructure is lending a helping hand to atmospheric science. EGI, with almost 200,000 computers spread across 400 sites, provides scientists with the computing power to do in-depth studies quickly and efficiently, offers data storage for post-analysis of output data, and steers collaboration between scientists and the grid experts. At the Aristotle University of Thessaloniki, we realized a grid computing case study driven by the scientific question of how climate change might impact on atmospheric pollution over Europe. Special emphasis was given on an important air pollutant, ozone. Although high up in the atmosphere, ozone protects life on Earth from the sun's harmful UV rays. At ground level, ozone is a health risk, the main ingredient of urban smoke, damaging crops, trees, and other vegetation. We know that ozone concentrations depend largely on temperature and solar radiation, and so it's likely that it will be affected by climate change. But how? To answer this question, we built an atmospheric modeling system comprising of two basic components: a regional climate model to simulate the evolution of climate, and an air quality model to reproduce the chemistry of the atmosphere, which is climate dependent. These two model components are coupled with an interface. 3 different sets of simulations were carried out throughout this experiment. The first simulation was representative of the present climate and covered the time period from 1991 to 2000. The simulation served as the control run. The second and third simulations covered 2 future decades, a mid-century and an end-of-the-century decade. The spatial resolution of the study was set to 50 kilometers and covered the whole European continent with a 3-hourly time resolution. The simulations were performed on the last grid resources. A command line interface to submit a DHE job to a specific EGI site was used. This job consisted of 3 sub-jobs executed in sequence, one for each decade modeled in the study. Grid computing allowed performing a 10-year time slice within only 20 calendar days. Each time slice required approximately 1 terabyte of data. Results of this work suggest that changes in summer surface ozone imposed by climate change until the mid of the century will be small, below 1 part per billion, but will be more pronounced by the end of the century, especially over southwest Europe. The median of summer near surface temperature for whole Europe was projected to be 2.7 degrees higher, with more intense temperature increase simulated for southern Europe. More demanding and elaborate studies of climate chemistry interactions are already underway, with even higher spatial and temporal resolution, with more sophisticated modeling system including complex atmospheric feedbacks, and all this thanks to the increasing computing power and storage resources made available by the EGI.